All right, greetings everyone. Welcome to the third part of the video now for section 3.2, just finishing off a couple of things. Okay, so let's go back to finding horizontal intercepts for a quadratic function. And we've talked about one technique for finding horizontal intercepts, which is factoring. But let's look at what happens if you cannot factor the function that you're given. So for example here, we have a function that we're calling k of x, which is given by the formula negative x squared minus 2x plus 5. We know here to solve or find the horizontal intercepts, we need to set this equal to 0. So we'd have 0 equals negative x squared minus 2x plus 5. And we could try to factor this. And we notice that the a value here is not 1, it's negative 1. So that tells us we try to use the AC method here. So we do a times c, so we do negative 1 times 5, which would give us negative 5. Then we want to find two numbers that will add, or excuse me, multiply to negative 5 and add to negative 2. Well, if we think about things that multiply to give us negative 5, there is positive 1 and negative 5, or negative 1 and positive 5. And those are the only options, and we can never pick one of those pairs and get negative 2. So this shows us that this one does not factor. So we must have a different method for finding the horizontal intercepts. And that method that we have, as the title of the slide here says, is the quadratic formula, which you may already be familiar with. So it tells us if we're trying to solve a quadratic for a 0 or a horizontal intercept, we can use this formula given by x equals, and of course I'm using x here because that's the variable in my equation. If there was not x's, I'd put a different one there. So it's given by negative b plus or minus square root of b squared minus 4ac, that whole thing being divided by 2a. Okay, so that's our quadratic formula. Note, and this is something you need to be careful about if you plug in your calculator or you're working with it, this division sign here, the fraction bar, is underneath the whole thing on the top. So it's not just underneath the root or underneath the b, it's underneath that whole thing there, okay? All right, so let's use this now with the equation we're given. So first of all, let's note what the values are for a, b, and c. So it's like a is negative 1, b is negative 2, c is 5. Let's go ahead and plug this in. So we'll have the negative of negative 2 plus or minus square root of negative 2 squared minus 4 times negative 1 times 5. Okay, all divided by 2 times negative 1. We can go through and do some simplifying here. So we have negative, negative on the first two there. That makes positive. So we'd have 2 plus or minus under the root. Negative 2 squared is positive 4. Minus 4 times negative 1 times 5. That would be plus 20. All divided by 2 times negative 1 is negative 2. And then we can simplify into the root there. So we have 2 plus or minus square root of 24 all over negative 2. And notice the root of 24, first of all, that will not come out nicely, right? We won't get an answer like 3 or 5 or something like that. So we can use techniques we've learned earlier about simplifying these roots. I won't go all the way through that right now, but I believe this one comes out to be 2 root 6. So our answers here for x are 2 plus or minus 2 root 6 all over negative 2, which we can leave our answer like that, or because we note that everything here is divisible by 2, or all the coefficients are, we could divide all those by 2. So 2 divided by 2 is 1, 2 divided by 2 is 1, 2 divided by 2 is 1. So it's going to become 1 plus or minus 2 root 6 over negative 1. And we could leave our answer like that if you wanted to. Okay, So that would be fine. Or actually, you know what? I just lied. I just lied to you. I totally lied to you. We cannot leave our answer like that because we're finding horizontal intercepts. So we actually need to write some coordinate points here. And so a couple things to notice about this answer. First of all, it represents two different numbers, right? That's what the plus or minus tells us. So what this is saying is that one of our answers is x equals 1 plus 2 root 6 all over negative 1. And one of our answers is 1 minus 2 root 6 over negative 1, which we can use those to then make coordinate points for our intercepts. So we could have 1 plus 2 root 6 over negative 1 comma 0, or 1 minus 2 root 6 over negative 1 comma 0. Okay. And again, it's okay to leave the answers like that. If you wanted to get some decimal answers, you could very carefully put this into the calculator. Okay, and again, I want to be very careful because for each of these, it's the whole numerator here divided by negative 1. So we need to keep that in mind when we put it in the calculator. So for the first one, when I do that, I get my horizontal intercept here as being negative 5.899 comma 0. And for the other one, we get 3.899 comma 0. Okay, so those would be our two horizontal intercepts here. Awesome. All right, one more thing from this section. Let's look at an application problem. And so our good friend Beyonce, which she is our good friend actually. She calls and checks in on how the class is going every week with me. She wants to enclose a new space for a garden. It's a rectangular space. And she's purchased 80 feet of wire fencing that she's going to need to enclose only 3 sides. Then the 4th side will be put against the backyard fence. You can kind of see that in the picture here, right? So here's where she'll need fencing. But the back part there, that's going to be up against the fence that already exists. We're asked to find a formula for the area enclosed by the fence if the sides of fencing perpendicular to the existing fence have length L. And then once we have that, we need to find the dimensions of the garden with the greatest area. Okay, so we're kind of trying to maximize area here. So lots of things going on with this. So let's first of all talk about, since we're trying to maximize the dimensions, oh, and here it says to find a formula for the area. Let's do that. So how do we find the area of a rectangular shape? All right, that's given by length times width. All right, so we see our length and our width over here. However, in order to maximize this, we can't really work with this equation, or this equation, because we have 2 variables in it, right? There's length and width. So we somehow want to change things or manipulate this somehow so we can get this into being just 1 variable. And the way that we can do that is use the other information we have. So first of all, we're told that she purchased 80 feet total of wire to enclose the 3 sides. And so if we think about what that means in the picture, it means that the length of this side plus this side plus this side will be 80 feet. So we can set up an equation from that. So first of all, we'll note that this first side here is also L, since it's the same as the side across from it. So it looks like our distance around that we'll need wire is L plus W plus L. Okay, so again, just this amount plus this amount plus this amount. And because we have 80 feet of fencing, then the 3 of those added together will give us 80. Okay, so L plus W plus L equals 80, which hopefully makes sense because, again, that's just what we're using for the fencing. We can combine some like terms here. So we have W plus, and then the L and the L together make 2L. Okay, that equals 80. We can then solve for W by subtracting 2L on both sides. When we do that, we end up with W equals 80 minus 2L. And notice what that allows us to do now is we have an expression for W in terms of L. So we can go ahead and plug that in up here. So now what we get for our area formula is that area equals L times, in the place of W, we'll have 80 minus 2L. We can then distribute that L there through. We'll end up with 80L minus 2L squared is our area formula. Now, that's helpful for us because notice that what we've ended up with here is a quadratic, right? The largest power we have here is a squared. So that means we can use some properties of quadratics here to try to find the dimensions of the yard with the largest area. And let's think about how we're going to be able to do that with this equation. Okay, so first of all, I could actually rewrite this as A equals negative 2L squared plus 80L. And notice in this case, the A value in this quadratic is negative. And think about what that means then for the graph of this quadratic. Okay. Well, we know that the graph of a quadratic looks like a parabola. Usually it looks like this. But the fact that this value right here for A is negative, how is that going to change things? Right, that's going to flip it over. Okay, so it's going to look something like this. And notice that if we do that, we have a local max in the picture now, which is helpful because we're trying to maximize, we're trying to find the greatest area, which means we're trying to maximize the area. And notice, where is that max occurring? All right, it's occurring at the vertex, right? So to find the dimensions of the largest area, let's find the coordinates of the vertex. So we know how to do that. We know that that comes from h and k, where h comes from negative b over 2a. And looking over at our equation here, we know the value for a is negative 2, for b is 80. So then we will have negative of 80 over 2 times negative 2, which gives us negative 80 over negative 4, which ends up being 20 is our value for h. We can then plug that in to our equation here to find the value for k. So we get negative 2 times 20 squared plus 80 times 20, which, if we work that out, it gives us 800. Okay. So we have that our vertex here is at the point 20, 800. And let's think about what these things represent here. Okay, and this is where it comes in really important that we start to understand what inputs and outputs are and how they're not always x's and y's, right? So this 2800 is the coordinates of the vertex for our function over here. But what do they represent? Well, in order to answer that, we need to think about what our inputs and outputs are for this function. And we're working with the area function over here. There's the inputs here are L's, so that 20 value there is an L. The output values are A, so that 800 is an A. So what that's telling us then is that the area of the garden is maximized when the length of the garden is 20, and in this case we're talking about 20 feet because those are our units. And when it's maximized, the maximum area there would be 800 feet squared. However, that does not answer our question yet, right? Because we're trying to find dimensions of the garden. So we have the L the length dimension, what are we still missing? Right, the width. And luckily we have a formula that relates W and L, right? If you remember back a few minutes ago, we had that W equals 80 minus 2L. So if we plug in our value for L here, our maximum value, work that out, we end up with 40 as our value for W. Okay, so it looks like based on that, our dimensions that maximize the area for our garden would be 20 feet by 40 feet. Okay. All right, that's it for now. I would suggest maybe going back in the video and rewatching for this last problem because I know there was a lot that happened there. All right, thank you for watching.